Newton's second law example. Here we have an elevator. In part A, it's accelerating down. So I have the elevator drawn as a rectangle. Its mass is 1,800 kilograms. Once again, if you calculate the weight by W equals mg, you take the mass, 1,800 times g of 10. The force of gravity will be 18,000 newtons. To find the weight, you just take the mass times 10. There's a cable on here that is pulling up or holding it up to at least to a degree. And when you have ropes and cables, we call that force a tension force. Ropes can pull on things they can't push. This rope is pulling up, but it's not pulling up hard enough to equalize the gravity. The gravity's, in a case, winning by a little bit, causing acceleration. The acceleration here is down in part A. The acceleration is down at a rate of 0.8 meters per second squared. Now that's an acceleration vector. I'm not placing that on the diagram with the forces. But so we'll apply Newton's second law to this elevator. That is F net equals ma. F net is always the big force minus the small force. In this case, it's accelerating down, so that has to be the bigger force, 18,000 newtons, minus the upward force of tension equals the mass, 1,800 times the A of 0.8. Now if you do the math here, you have 18,000 minus T equals, well, it's 1440, but we'll need to round that off to 1,000 because I'm going to need to combine that with the 18,000, and the 18,000 is only good to the thousandths place. So I've rounded that off to 1 sig fig, as you'll see here as I move things around. As I move the T around and solve for T, I end up with T equals 17,000. I can't subtract the 440 from a bunch of zeros in the 18,000. So the answer is 17,000 newtons. It's a little bit less than the downward force because it's accelerating down. The net force here is 1,000 newtons basically in the downward direction. Now in part B, the acceleration is up at 1.2 meters per second squared. But I'm going to still apply Newton's second law, F net equals ma. So I have F, let me use black, F net equals ma, but when it's accelerating up, it's still the same diagram. We still have the force of gravity down, but the tension force is bigger now because some mechanism at the top, some motor is pulling harder to pull this thing up to accelerate it upward. So now, here's how the problem changes. F net is T minus 18,000 equals the mass, 1,800, times the acceleration, which is 1.2. That brings us to T minus 18,000 equals 2,000, rounded off to the nearest thousand because I need to combine that with the 18,000, and you end up with T equals 20,000 newtons because the upward force now is bigger than the downward force, causing the upward acceleration. And finally here, we have the elevator moving at constant velocity. It doesn't say whether it's moving up or down, but it doesn't really matter because to move at a constant velocity, this is one of those that's so easy it's hard. The answer has to be in part C that the tension must equal 18,000. The hard part about this is somebody might say, well, if the tension in a cable is 18,000 newtons, it seems like the elevator is not going to move. Well, if it's not moving, you're correct. It will not get moving. It will stay stopped if the two forces are equal. But once the two forces are not equal, it will accelerate. But once it's moving, if it's moving and you've got it up to a certain speed, and then you manipulate the tension like the motors do, and it's already moving, it will stay moving at that speed. If you equalize the two forces, it will no longer accelerate, but it won't decelerate either. So when the two forces are equal, you either have constant velocity, like in this case, and I don't know if I'm moving up or down, but it's a constant velocity. It's not accelerating. Or you could have been at rest, but you're not at rest. You're moving with constant velocity in this case because you were told the information. All right, one more example. Here we have a car. And since I'm good at drawing cars, I drew the car for you already. It's 2,100 kilograms. You could draw the car as a rectangle. You don't need the tires like I do. You don't need, a good-looking car like I have. But here it is. Now, the free body diagram is where you start these problems. And there are some other ways of doing this problem, but we're going to use Newton's second law. And once again, with all these Newton's second law problems, you want to draw the free body diagram, beginning with the most obvious force components, and that's the weight. It's 21,000 newtons down. And the road is going to support this car upward. Now, the road contacts the car in 4 different spots, the 4 different tires, but it doesn't really matter where I draw that force arrow. It's going to be an upward force from the road on the car of 21,000 newtons. Unlike the elevator in the previous problem, which was suspended in the air, this is a car sitting on a road. It's going to be supported, like the boxes were supported by a 2,100 Newton force. But those forces will not play into this problem, even though I drew them as part of the diagram. They're going to cancel. They do not cause any kind of acceleration. Now, if the car is moving to the right, doesn't really matter which way it's moving, with a speed of 25 meters per second, we want to stop the car. Now, you hit the brakes, and the brakes are, well, they're not that complicated, but it's hard to show a detailed picture of the brakes in a diagram. But the net result is, if the car is going to the right and you hit the brakes, what that does within the tires, and we're ignoring air resistance and all that kind of stuff here, the major thing that's stopping the car is a frictional force, okay, braking force. I'm just going to call that F. You can call it force of brakes, but it's a force that's stopping the car, that's working through the tires, through the inner parts of the tires and the wheels. All right. Now, that's the only force working horizontally. So that makes the problem easy when I'm going to apply Newton's second law. But you'll see one little issue here. When I apply Newton's second law here, F net equals ma, F net equals ma. Well, F net is just F. There's one force stopping the car, so it's just the one force is the net force. F equals 2,100, the mass, times the acceleration, but we have two unknowns. Well, we have to go back a couple weeks ago just to the basic definition of acceleration, or you can go through the whole uniform acceleration equations, but if you go back, and I'll go down lower here, to the definition of acceleration, acceleration is delta V over t, which is basically the first uniform acceleration equation. A is going to be delta V. The delta V here in this case is going to be 25, technically negative 25. The car is going to start at 25 meters per second and then come to a stop. So the change in velocity is going to be 25. You don't need to worry about the negative. I'll talk about that. In a time of 4.5 seconds. So the acceleration, and those are all standard units, that's meters per second divided by seconds. So we're going to get an acceleration here of 5.6 meters per second squared. So therefore the braking force, the force that has to stop this car, is equal to 2,100 times the acceleration of 5.6. And if you want to put in a negative 5.6, you can. You don't have to. That just means it's a negative force. It's opposing the motion. We don't really need that. We have all the arrows in the diagram in the proper spots. And it turns out that F, the braking force, the average braking force, and once again, don't let the word average scare you, because when a car stops, the force might not be consistently uniform. It's just that on the average, it's going to be this particular force. It comes out to be 12,000 if we round off to 2 sig figs, which this whole problem, that's the nature of this entire problem. My calculator says 11,760. Round off to 2 sig figs here. The stopping braking force is 12,000 newtons.